Hello, welcome to Autodesk NetFab Simulation Lesson 1, Workflow Summary. So what I want to cover in this lesson is, before we get into actually using the software in later lessons, I want to explain just at a high level what the software is used for and what the workflows are, so that when we get to using the software, you can understand why it is we're doing the things that we're doing. So mainly I want to demonstrate the NetFab Simulation multi-scale modeling approach. I want to discuss the inputs and outputs of NetFab Simulation, and I want to demonstrate common failure modes that NetFab Simulation can be used to predict. So when we started developing NetFab Simulation, the goal was to be able to predict any common failure mode brought upon by excessive distortion or residual stress. And a couple examples are right here. So this is an example where a part actually distorted to the point that it delaminated from its support structure and the build failed. And here's another part that actually distorts upward in the build direction through the top of the powder bed and gets hit by the recoder blade when it goes to rake a new layer of powder. That part got ruined as well. So the idea was that because these trial and error iterations that it takes to get a successful build are very costly, it would be more cost effective to run a thermal mechanical simulation before actually going to the machine. So if you know your machine process parameters and you know your material properties, you can input those into a heat transfer analysis to calculate the temperature of the part at all of the nodes during the entire build process. You can then take those temperature predictions and feed them into a mechanical response calculation and calculate the deformation and stress of the part during the entire build process. And then you can look at that final product and say, is that something that I really want to build, or does it need some more design iterations before taking that to the machine? So what we wanted to do originally with NetFab Simulation is the goal was to be able to get very fast and accurate results on high-end desktop computers. So the way we approached this problem was we actually split the analysis into two scales. The first scale that we have is a small scale detailed scale. So this piece of material is a millimeter by a millimeter. And what we're going to do at the small scale is we're going to take a material and we are going to run a moving source simulation using a set of machine process parameters like your power, scan speed, layer thickness, etc. And so if I'm depositing, say, Ti64 in an EOS machine using the performance settings, I would in this scale put in the material properties for Ti64, and I would input the power, scan speed, layer thickness, so on, that EOS uses at their performance settings. And what we're going to get from this scale is we're going to get an understanding of how a particular material thermally and mechanically responds to a particular machine parameter setting. And we're going to get an understanding of how the individual layers mechanically interact with one another. Once we understand that for this combination of material and parameters, we're going to store that information in something that we call a process parameter file, or a PRM file for short. Now, once we have that PRM file, we can take this information and we can actually start to stitch some of these blocks of material together. And then since we also got an understanding of how the layers are going to mechanically interact with one another, we can start to pile those layers up and actually map those onto a geometry. So now, while this scale was a millimeter by a millimeter, this scale is 240 millimeters along this dimension. So this is taking almost the entire build volume. And now we can start to take this information and map the thermal and mechanical response onto a full geometry. You can actually see it building in situ. And now this scale, this example here ran in 4 hours on my 14-core Autodesk issued desktop. So very fast run times. Now, just to break this down a little bit, basically, this is just going another layer deeper. We've taken our material properties listed here, and we've input that into NetFab Simulation along with our machine process parameters. And the output is a process parameter file that's unique to this material and process parameter combination. Now, once we have that parameter file, say for the EOS machine's performance settings on Ti64. Now, anytime I go to build a geometry on the EOS machine using the titanium, using the performance setting, I can use this PRM file, input this into NetFab simulation along with the CAD file, and the output will be the distortion of the part that I'm going to build. Now, in addition to just getting the distortion predictions, which are useful because you can look at the part and see if it's distorted out of tolerance, you can also use those distortion predictions to predict other common failure modes. So this example that I showed at the beginning of the presentation of a part that actually deflected upward into the recoder blade, now we can use these distortion predictions to investigate why it is this happens, and if we had run this before building, this can be predicted and mitigated. So you can see here this overhang in this part actually lifts up in the positive Z direction in the simulation, and it actually outputs a warning that says basically, careful, you're going to hit the recoder blade. And now a design engineer knows that if this feature isn't critical, they should probably redesign it, and if it is critical, then you should probably anchor that down with some support structures. And another common failure mode shown here is this part delaminates a bit from the support structure. And so now the user can prescribe, we can actually simulate the full part here and the support structures, and we're going to prescribe a failure stress at the interface between the two. And if that's exceeded, the elements will fail. So you can see as that stress got exceeded, those elements in that zone failed. This distortion is magnified by something like 10 times, which is why it looks so dramatic. But we can say that in that area, you may want to strengthen the support structure to anchor this part down. Another useful output from NetFab simulation is compensated preforms. So the idea behind distortion compensation is that if I have this preform, and this is what I want to come out of my machine, that's probably not what you want to feed into the machine to get this result, because when I feed this into the machine, the simulation can tell me that I'm actually going to get some pretty severe distortion. So now we can use those distortion predictions to actually change this preform. We're going to offset it in a way that once it distorts, you'll actually get the shape that you want. We've actually built these parts. This is a example of the part built using just the nominal geometry, and you see you get some distortion in this region, but then when the part is built using the compensated preform, you can see that you get much less distortion along this interface. So distortion compensation is a very useful tool to combat this problem. So that's what I wanted to cover in the first lesson. In coming lessons, we're going to actually get into using the software, but what we covered today was we explained the NetFab simulation workflow. We introduced the concept of a PRM file, which is very important. We discussed how results are mapped from the PRM scale onto the part level scale to get fast and accurate results. And we just demonstrated NetFab simulation's predictions of some common failure modes in additive manufacturing brought upon by distortion and stress. So in the next lesson, I want to actually cover how to generate our own PRM files so that we can get on to actually running our own simulations.